Hi kids, now we'll be going with this tunnel in the earth kind of question, which is combination of SHM and gravitation generally. So you can read the question. An alien spaceship is revolving around a spherical asteroid in a very low circular orbit. The period of revolution of the satellite is 15 minutes. So when it is rotating just above, you need to calculate the time period, that is 15 minutes, they said. A research party of the alien students land on the asteroid and drills a tunnel through it along the diameter, then launch a rock into the tunnel with initial speed equal to that of orbiting spaceship. How long would it be before the rock comes back to the launch point? So it's like this. Yeah, so before that, if we dug a tunnel inside that, let me say instead of asteroid, it is earth, asteroid, whatever it is. So if I dig a tunnel, and if there is the mass is going somewhere at a distance x from the center, then force will be gm, where m is the mass of the asteroid into small m is the, what is that thing, a rock. So where capital M is the mass of the asteroid and small m is the mass of the rock. So it looks like k into x. This mass is density into volume I am writing. So it looks like k into x form. So it looks like k into x from towards the center, towards the origin, where net force is going to be 0. So it looks like the force is of SHM form. It is in the opposite direction of displacement from the mean position, right? So then we can calculate the time period using SHM thing, but the only difference is when you are throwing it from here, you are not dropping it. If you are dropping it from here, it would have performed SHM like this. But when you throw it from here, what will happen? It will reach here with maximum speed, it will reduce its speed, but when it reaches here, it will still have some speed. So with that speed, it will go out and its speed will become 0 somewhere here, it will come back. So when it is outside, it is not SHM, because the force equation will be inversely proportional to r square. So from here to here it will look like SHM, but from here to here it doesn't look like SHM, but from here to here it looks like SHM, it will go up. Outside it is not SHM, inside it is SHM. So let us calculate this time period in two different ways. One is what's the time taken from here to here separately, from here to coming back separately, right? Now I can look at it like a part of SHM. So it is coming here with some speed. So if at all it was part of full SHM, this is only partial, right? So if at all it was a part of full SHM, I want to see what amplitude it would have been. So it looks like k into x form, right? So at this moment there will be potential energy half k into x square, where x is r. Potential energy plus kinetic energy half m into v square. V is given as just the velocity outside, right? Root of gm by r, half m v square. So that equals to half k into a square. Potential energy there plus kinetic energy there equals to half k into amplitude square. From there, when I do the manipulation, k value is this thing, right? K value is this thing. So when I do that substitution, I will understand amplitude is root 2r. The meaning is, if at all you throw it that particular velocity, it will be SHM. But if it was full SHM, the amplitude of that full SHM would have been root 2r. So once we understand that, I can plot this phasor thing. So I can say it is going from here to here, where it would have been a part of full SHM of amplitude root 2r, So if I want to calculate time from here to here, then I can easily see this angle will be 45 degrees, this is 90, this is 45. So it is moving by an angle 90 degrees. Basically 90 degrees in the sense 1/4 of the total time period. Total time period you can guess, right? Now this is kx from 2 pi into root of m by k. So 1/4 of total time. That is SHM thing. See what we have done, when you throw it, it is going to perform SHM from here to here. Now from here to this thing, it is not SHM, but from here to here it is SHM. From here to here it is not SHM, right? So basically we found what is the time taken from here to here. Now we are going to find what is the time taken to come back to this point. Now there it is going to be inversely proportional to r square, so we are going with this thing. So it is going from here to here and it is coming back. So this motion you can visualize it like a straight line motion. Straight line motion you can visualize it like a flattened ellipse. Now you can see, if you want to use Kepler's laws, it looks like a flattened straight line. You can see it like a ellipse, but that ellipse, one of the focus must be at the earth or like asteroid center. So we need to draw a ellipse with asteroid as one of the foci. Now for flattened ellipse, foci will be at the end, right? So if there is a flattened ellipse, then I can visualize the center asteroid concentrated here kind of thing. See, this is imaginary ellipse and imaginary shrinked thing just for our calculation. So I can visualize the straight line which is going like this and coming back as this flattened ellipse. So we need to calculate what is the time period for this flattened ellipse. For that, for time's sake, like let me say it's of some normal ellipse only. Anyway, if I want to find what is the energy will be, yeah, here potential energy you know, minus gmm by r, kinetic energy half g, yeah, energy conservation. By energy conservation, you will be getting the total energy as minus gmm by 2r. So from there, once you get total energy as minus gmm by 2r, then you will be getting the major axis of the ellipse is 2r. So once you understand major axis of the ellipse is 2r, this is already r, you know, so this is going to be r. So that's the idea. So you will be calculating total energy. From there you will be getting what is the major axis. Once you get the major axis, you will understand it will go to a distance of r and it will stop and it will come back. Anyway, that much you can manage. So now we need to calculate what is the time taken for this. That we are trying to visualize it this way. So if at all something is performing elliptical motion about this focus, then yeah, we need to calculate basically what is the time taken to go from here to here. So that's the same previous thing, right? Time taken to go from one minor axis to the other end of minor axis. Now aerial velocity is going to be constant. So for the total area, time is t. See again that thing. Why it is same t? It's the same t as SHM t, because time period is proportional to semi-major axis cube, right? Semi-major axis cube. When time period above, when it is rotating just above also, time period is proportional to semi-major axis cube. For SHM also, time period is proportional to semi-major axis cube. I mean, you will be getting the same thing. So time period when it is rotating just above Earth, time period is same as when it is performing SHM full time period. When it is elliptical motion also same time period. So I am taking the same time thing. So area covered by time taken will be same, aerial velocity. So total area by total time taken equals to, now this area I need to calculate. In order to calculate this area, so yeah, so if this is B and this is AE, this math thing you people will be knowing. So I need to calculate what is the area of this thing, which is pi AB by 2 plus area of this triangle by time taken. So from there I will be calculating what is the time taken to cover from here to here, that is what is the time taken for this entire area to cover. Now that's how it looks like, but in this particular question E is 1. It is flattened ellipse, right? E is 1. When you substitute E is 1, you will be getting this much time. Now what is this much time? This much time is the time taken to go from here to here. But what we need? We need this time plus this time plus this time plus this time. So basically we need 2 times of this and 2 times of that. So we need 2 times of this and 2 times of that. That's the total time, but they never ask. They are asking what is the time taken to come back, right? Yeah, comes back. So we don't need 2 times of this one, and yeah, so T1, T2, again T1. So we need 2 times of this and 1 time of this. We need 2 times of this and 1 time of this. Then you will be getting the option, right? Now the time period is same, and for everything it is 15 minutes, right? Thank you.